In the last video, what we did was we talked a little bit about how we can understand the relationship between the current in the thick wire and the current in the thin wire, and how that gives rise to differences in the electric field and differences in the speed with which the electrons move through the wire. And in that, we use this principle of conservation of charge, and in particular, we use the steady state assumption to describe that the current throughout this wire is constant. In this next video, what we're going to do is we're going to talk a little bit about the energy principle instead, and we're going to ask about what the energy usage is in this system. So the first thing we're going to do is we're going to essentially draw a boundary around our whole circuit, because we're going to consider the whole circuit our system. And what we're going to do is we're going to say, well, that system is closed in the sense that there are no influences from the outside, because we've included the battery, the wire, the resistor, everything is there. And so when we look at how the energy is used in that system, by closing the system off like that, we have the simple result of energy conservation. That is that all of the energy stays in the system, it just moves around to its different parts. And so that means that whatever energy is used by the battery, plus whatever energy is used by the wires, plus whatever energy is used by the resistor, all adds up, how those change, okay? And we have a way of thinking about that. This is a statement of energy conservation, but we have a way of thinking about that because what we have understood from early on in the class is that the energy associated with moving charges around has to do with the electric potential. And so to remind you, we can think about this in terms of the electric potential energy and how that is related to moving a single charge around in terms of an electric potential. And so it turns out that all of these energies that we have in our battery, or I'm sorry, in our circuit, can be associated with potential energies that are associated with the electric field, because each part of the battery, or I'm sorry, each part of the circuit has electric fields associated with it which set up either the charge separation or drive the charges through. So in fact, each of these is essentially thought of as an electric potential energy, and so we can look instead at a single charge and how the potential associated with the battery, the electric potential, relates to the electric potential associated with the wires, and how that relates to the electric potential associated with the resistor. And in each of these cases, we have some theoretical charge Q that runs around the circuit and picks up all this energy, but really that's a construct. We don't need it, because what we have is a statement of how the electric potential changes when we go around the circuit. So really, the change in the electric potential as we go around the circuit completely is zero, in a very similar statement to the total electric energy associated with the circuit. So what we have is a way of describing the electric potential by dividing out the charge. That is that the sum of the change in the electric potential associated with the battery, with the wires, and with the resistor is equal to zero. This is the so-called loop rule. You might have seen this in some of your engineering courses. So if we go around and we add up the changes in the electric potential, if we go all the way back around the circuit, we find that that sum is zero. This thing has the really nice property in that it can actually be measured in a circuit. So you can get a multimeter, you can get a voltmeter, and you can go and you can make measurements of this to verify it. One other thing I should say is that this is often the source of our energy, and these wires use it, right? So the mechanical battery model we have is essentially we're dumping energy into this to be able to move electrons around this whole wire where they come back. And so oftentimes, not always, but oftentimes we can think of this as sort of our source of energy for our system, and this is the stuff that's actually using it up in our system, which is how they sort of balance out. The last thing to say is when you think about this in terms of your engineering contexts, it's often the case that we want to know about how quickly does that happen, right? So the amount of energy is not so much of a big deal, but the amount of it that goes into an electronic component per unit time matters a lot, because those things can basically blow up if they have too much electric energy going into them too quickly. And so the thing that we want to be able to talk about in this context is what we would refer to as power, or in our case, electric power. And so power in this context is going to be how much electric energy does a particular element in your system use per unit time. So really for us it's this idea of the current times the voltage across whatever that element is. This gives us a sense of how much energy is there, and this gives us a sense of how much charge per unit time is crossing that, which together gives us a sense of exactly something that is the amount of energy per unit time, or the amount of watts that that circuit element is using. There are lots of different ways of rewriting this. This one is the one that's kind of the one that's most appropriate for thinking about an energy associated with the amount of stuff per unit time that's crossing a boundary. So that's the one we'll use. So in this video, what we did was we used that idea of energy conservation to derive the loop rule to understand how energy is shared throughout a system. And then what we did was we talked a little bit about why you would care about power. That is, how much energy per unit time is sort of dumped into a circuit element.